Okay, let's get started. Thank you for being here. I have titled these slides Microarchitectural Side Channels and Transient Execution Attacks. And basically in these slides, we'll first go over some performance optimizations in modern architectures. We'll take a look at what a modern, say, Skylake style processor looks like. And then we'll start talking about microarchitectural side channels, why these exist. We'll look at two of them in a little bit more detail, prime plus probe and flush plus reload. And I believe these should cover enough information in the microarchitectural side channel domain that you should be able to understand any other variants that you come across. And I list a few of them and we'll briefly discuss them as well. Then we'll move over to transient execution attacks, specifically Spectre and Meltdown. There are several of them, but we only have so much time. And in Spectre, we'll take a look at an actual example, which works. Like we'll take a look at some code and we'll go over some interesting bits of that code and see why that works. And the key takeaways that I want you guys to have at the end of this talk is, first, you should be able to understand why side channels exist, why transient execution attacks are possible. You should understand what are the components required for a successful attack. Like what are the things that you need in your program that together would give you a successful transient execution attack. And then you should know enough that you are able to read related work and understand it and understand the future attacks that come in. So I hope that these slides today will give you some good background for that. Okay, so this is what a diagram of a Skylake style processor looks like. So this is from the MDS Attacks website, where they basically read a bunch of patents, they read some documentation by Intel, they read some other reverse engineering documentation, and they just put it together what this basically looks like. So you can see it's fairly complicated, and a lot of these things exist just to make programs faster. Like that's simply the case. So for example, let me turn on my laser pointer. Okay, so consider this thing, micro-op cache, right, which exists in the front end. All this micro-op cache does is it stores some decoded micro-ops, right, so that they can be served quickly. Or take a look at this load buffer and store and forward buffers. These exist so that if you have loads and stores going to same addresses, you can forward them instead of going all the way to memory and coming back. And then you have a lot of caches. You have instruction cache, you have data cache, you have L2 cache, then you have LLC, and then there are several other caches that exist in the system. So these architectures are fairly complicated, and they're designed to primarily improve your IPC. And these give rise to microarchitectural side channels. Now, before we get into it, like a very simple clarification, covert channels are intended communication between two parties where you want two programs to communicate. And side channel is when there is unintended communication, right? There is one program which is just operating on its own, and then by the virtue of its hardware utilization, it is leaking some data, and you're able to understand this. And the system guarantees memory isolation, and I use the word system very loosely here, but this memory isolation is only enforced at the software level, right? At the software level, you have different address spaces, right? And they're not supposed to interact with each other, and most of the time they work. But when you go to this hardware level, there is no notion of what is program A, what is program B, or what is the separation between these two. These are all shared structures. So what side channels are very basically, they are data-dependent utilization of shared hardware resources. If you don't have data-dependent utilization, then your program is what is known as data oblivious. In that case, the footprint when somebody is observing the microarchitecture will look exactly the same because there is no data-dependent behavior. If the resources are not shared, then there is no way for one program to interfere with another program's execution and get that information out. So you need both these components. You need data-dependent utilization and you need shared hardware resources. Yes?
As a programmer, you have the choice of writing your program as data independent.
Right.
In which case, even the vulnerabilities in this hardware would not be able to infer anything about your secrets if you did that. And you just take an efficiency hit because data independent programs, you basically can't use any heuristics. You can never make a decision on data directly.
Exactly, yeah. Okay, so if you recall from 573 lecture 5, these side channels are then facilitated by modern hardware design features. If you have shared hardware resources, then you have contention in hardware. What that means is that your hardware only has a limited capacity. Say if you're talking about a cache or if you're talking about various execution ports, there are only so many of them because your hardware needs to be a finite size. So if there are shared resources, there is going to be some contention, right? And that can be observed. Then what you do is you optimize a lot of common case operations, right? That's the main lesson you also take from 470, that optimize for the common case, design for the common case. All we care about in the uncommon case is that we want correctness. So what that results is that the edge cases or the rare operations, they are incredibly slow compared to the fast operations which have been optimized. And finally, modern architectures provide counters for performance visibility. This is very important to, say, people who are building data centers or who are building very large scale applications because they want to exactly figure out where their application is slowing. So you need to provide these tools for people to analyze their programs and figure out why they're slowing down. And if you provide high performance visibility, I can very easily compare the common operations and the slow and rare edge case operations. And that difference, which I can amplify using other techniques, all that really helps me cause these microarchitectural side channels and leak data. So these channels, they exploit several strategies. One is you have limited storage space, say in a cache or in a branch target buffer. There are only so many entries where you can write your data. And these entries contend across different processes. So there you're able to leak some data through contention. There can be limited bandwidth. So for example, you have only so many execution ports, and if all the programs are contending for the same execution port, then one program will execute while the other will take some time. So you can figure out, say, which execution port my application is trying to use. Sometimes you can also target additional optimizations. So if you remember from the 573 lecture, there's the AVX units attack, where essentially the AVX units are powered down if they're not used after some time. And then if they are used recently, then they're powered up. So if they're powered up, they'll be accessed quickly and operations will proceed quickly. But if they're powered down, it'll take a while to power up and then do the operation. So this huge timing difference can be exploited. So behind all side channels, the key idea is that you take your shared resource and bring it to a known state. You know what it looks like, say, for example, if you're talking about a cache, you know exactly what data is in my cache and which cache sets it's located in. Then what you do is you wait for the shared resource to be utilized. Once it's utilized, then you analyze the shared resource's new state. And then you compare what was the difference between the original state and the new state. And that way you can infer information. So caches are very popular targets. I have been talking about caches, and that's primarily because A, they are ubiquitous and they are very powerful. They offer a lot of performance benefit. And then you can see that there are caches for data. There are caches for instructions. There are caches for address translations, which is the TLB. There are caches for there are caches for translated instructions as well, which are your micro-op caches. And there are caches for stores and load. So caches are all around there, like very prevalent. Then it's easy to achieve and exploit sharing as well. So this is because cache organization, its size, its indexing methods, inclusivity, and all the indexing strategies they are either known or they have been reverse engineered. So caches are very ripe for attacking. And then it's easy to measure performance impact as well. That's because your caches offer a lot of performance improvement. If something is in the cache, it'll be served hundreds of cycles quicker than something which is not in the cache. And with the help of all the performance monitoring units that we have, you are able to measure this. You are able to measure these differences often at a very fine grain. So, and caches, by the way, are not the only things that are targeted for microarchitectural side channels. You can target any buffer you find in the microarchitecture. You can target your branch prediction units. You can target the coherence logic, the replacement logic. We saw a paper like that in the security portion of the class. You can target memory disambiguation units, which are doing predictions. You can target your floating point compute units, like with the AVX2 attack, and then you can do attacks on DRAM. So basically, anywhere you have data-dependent utilization of shared hardware resources, you will have microarchitectural side channels. So let's take a look at one of the side channels. This is the prime and probe timing channel, where what you need to know is that you have this shared cache. It is organized into a number of sets and a number of ways. And the prime and probe timing channel, it operates on cache sets. So what they do, what happens in this case is there are two processes, A and B, and they can communicate with each other or infer each other's data by contention in specific cache sets. So what does that look like? So let's say process A is using the cache and it puts some of its data in the cache and it knows that it's using set S1 and S3. So this is operating at set granularity, right? And then it has brought this shared resource to a known state, as we saw. And then now it will wait for process B to execute, where what process B will do is it will use some different cache sets and then one cache set where it contends, right? So process A is waiting for process B to execute, and then process A will monitor its own cache state and it'll figure out what the new cache state looks like. So for example, the data that is in the cache, that is read quickly, but the data that is not in the cache has to be brought from the main memory. It'll be put in the cache and then process A can access it. So this timing difference is what is available to process A. And with that, process A knows that, okay, process B's algorithm is using set 1, right, in the cache. And that way you can leak a lot of information. So yeah, you monitor specific cache sets for evictions. And these timing differences, they have a lot of uses. You can, steal encryption keys because the algorithm is public, so you know exactly which cache set is being used. So once you know that, you can figure out, okay, that set 1 is being used or set 3 is being used, and that directly gives you information about the encryption key. Then you can use it to capture keystrokes. You can use it to fingerprint any application that's running. You can exactly understand its cache utilization. You can figure out, if I'm on a shared server, I can figure out which applications are running. If I have like a prior model I can compare against. And then of course, these are used for facilitating transient execution attacks, as we'll see a little later. And this is what it sort of looks like in practice. This is just a figure I generated. So on the x-axis, it's just time intervals. And on the y-axis, there are different cache sets. So this is for L1, so it's basically set 0, set 1, set 2, set 3, all the way up to set 64. So as you can see, the dark lines, they indicate cache hits, and the light colors, the white and the green, they indicate cache misses. So here you can see that I can get certain patterns for cache hit and cache miss, and through set A, I'm transmitting like 1, 0, 1, 0. So this is like, I'm transmitting bit 1 during this epoch, I'm transmitting bit 0 during this epoch, bit 1, bit 0, and so on. And then using another set, I can communicate more information. Yes?
Are those two lines, those two dash lines, two separate threads communicating with each other?
No, this is just one process measuring the cache activity. Now, this can come from just one program which is trying to communicate with it. This can come from multiple programs. It depends on how you want to do it.
The black is hits, and then between the
Yes.
black parts, it's missing all the time.
Yeah, exactly. So yeah, so that's sort of, this is trying to give you a visual idea of what the cache activity looks like, and that's how you can, leak some information. So any questions on prime and probe so far? Yes.
What's that black line across the whole thing? What's that? Is that like
that's
an uncached line or something?
Yeah, that is something. So this is something that I observed when running. So some cache sets always show hits. It's either the data that is just being used to keep the program running.
Black is hit, right?
Yeah.
I thought it was miss. Okay.
Oh, sorry. Did I say miss? No, black is hit. So
No, you said the right thing. I misunderstood.
Oh, okay. So yeah, so some cache sets will always show that. Sometimes you see these very nice patterns, which I spoke to someone who works in this space, and according to them, it's prefetching effects, but I haven't been able to quantify it exactly. But basically the caches, even though there's a lot of activity going on, this is, by the way, activity from a lot of system operations, you're still able to see clear communication by different programs. So that's intuitively what
That's a
this looks
strided
like.
access, right? Because
Yeah.
over time, you're incrementing the set.
Right.
Yeah.
Yeah. So, cool. Okay, so that's prime and probe. Now let's look at the flush and reload timing channel. So in this case, what happens is these processes communicate at the cache line granularity. They don't care about cache sets anymore. And they can communicate on cache line granularity because these cache lines are shared. Right, you can exactly control access to this cache line or this cache line because they're shared between the two. In the previous case, there was no sharing. The sharing was limited at the set granularity, just wherever your data is landing in the cache. In this case, this is shared memory. Both the processes have access to it in their own respective address spaces. So this is what it looks like. Let's say the cache has these two cache lines which are in there. And then what process A is going to do is it's going to flush these lines from the cache. So now they don't exist in the cache hierarchy. So as I mentioned before, this is bringing the shared resource to a known state. Now it knows what's going on. Then it'll wait for process B to run, where let's say process B is using one of the shared cache lines and it just loads this one, right? So process A has waited for process B to execute, and then process A will execute again, and then it'll try to see which of the cache lines are already in the cache. So this one was already in the cache because it was loaded by process B. So that was accessed quickly. This one was not in the cache. So that was accessed slowly. And that again leaks some information about how process B is operating or what process B is doing. And the applications for flush reload are very similar to prime and probe. You can leak the exact same information. The only difference is you need shared memory for this channel to work. But if you have the shared memory, it works at a much finer granularity, whereas prime and probe, you don't need shared memory, you just need eviction and cache sets, but then it works at slightly coarser granularity. So there are trade-offs between flush reload and prime and probe and several other types of channels which can tell you about, and you can decide which one to use based on the application you're trying to attack. So this is what it looks like in practice. So with prime and probe, we saw covert channels. So with flush and reload, let's see a side channel implementation, where basically you have these square and multiply algorithm. This is, okay, so now it's been fixed because this problem has been known for, 25 years now, but it's still a very good, it's a very good way to show how your cache channel works. So basically what you need to know here is that so this EI bit is the bit which is supposed to be secret. It is part of your key, your encryption key. And if you can leak these bits, and if you can leak enough of these bits, you can do some sophisticated cryptanalysis and you can reconstruct the entire key. And what that does is it reduces the search space from which would take, I don't know, hundreds of years to, maybe a few hours if you have enough bits. So anyways, the idea is that you do this square and reduce operation for, whether, if your exponent bit is 0, you just do this. If your exponent bit is 1, then you do an additional multiplication and reduce operations. And this is what it looks like. So basically here, these are the shared cache lines. And you see that, okay, these cache lines are in the cache. So that means a square is happening, reduce is happening. And then if I detect this pattern, I know that's a bit 0. Then again, square is happening, reduce is happening, with 0. And then I see square, reduce, multiply, reduce. Then I say, okay, that's 1 because I know what the algorithm looks like. So a key thing to know here is that the crypto implementations you're attacking, the algorithms are open source, right? You know exactly what the algorithm looks like. The only thing that is secret is the key. And this is how you can leak the key. So that's what this looks like. So this is from the flush reload paper. Any questions on flush reload?
Just a comment. Like this paper changed the way they configure virtual VMs in cloud environments. They basically don't let you share any physical storage for instructions between VMs now, right?
Yeah.
So before this attack, if you and I were both running Linux on the same VM, we'd have the same code pages. If it was the same, that's why they, try and push everybody onto the same release. Post this attack, 2 copies.
It's called page deduplication.
Deduplication.
Yeah,
It
you
sounds
want
like
to-
a feature, but it's actually a.
Yeah, and you initially had duplicated pages because all of these pages cost memory. And if you just have one page, a common page which everybody's reading from, then you're fine, right? And then they use this optimization called copy on write, where basically you only create a copy of the shared page when you're actually writing to that page, so you need a new copy. And all of these, and see, the idea behind these side channel attacks comes back here as well, because page deduplication, it's an optimization. It makes the common case really fast. And then if I'm actually making changes to the shared page, all I need to make sure is correctness, right? Even if it runs really slow. But if it runs really slow, I as an attacker can observe some very interesting things in the microarchitecture. So that's how these things work. So yeah, so that's flush reload. Now there are several other timing channels. Like one example is flush, where basically it's just timing the execution of flush instruction, like how long it takes to flush data from the cache. If data is in the cache, it'll take a long time to flush. If data is not in the cache, it will abort early. Right, and then you can very easily measure this timing difference. And this is a very popular attack because it's very stealthy. So what that means is that some defenses, they try to measure cache evictions. They try to see how many evictions are happening, and if it's, say, above a certain threshold or in a certain pattern, they're like, okay, we are under attack, so we need to do something. This thing causes much, much fewer evictions, so it's a lot more stealthy. That's like a flush attack. There's an evict time attack, which is much more coarser than the prime and probe attack, where effectively what you do is you time how long a process usually takes, and then you just evict a particular line from the cache set and then see how long it takes again. So if it takes the same amount of time, then you know that the process you're attacking, it didn't access the shared line. But if it takes more time, then you know that it is accessing that shared line, so you leak some information. There are cache occupancy attacks, which basically use this prime and probe and evict time type strategies, and these are even coarser, where they are priming and probing the entire cache. So you basically prime the entire cache, you wait for the program to execute, you probe it to see what changes happen in the cache. But these are, as I said, they're coarse-grained. You need expensive offline analysis because you need to understand what it means when, n number of cache lines are evicted or n number of cache lines are brought into the cache. So these are very interesting, but they require a lot of offline analysis. And then there are some more, attacks which are evict, reload, prime, abort. And now I think once you look at those papers, you'll exactly understand what's going on and why they leak. Okay, so we've been talking about caches, but those are not the only things that leak. And this I will go through a little quickly. So, for example, a very popular attack that came out recently was through the processor front end. So the idea here is that I can have the instructions that are decoded. They can either be served through the micro-op cache, which will be served very quickly, or they can go through this long latency pipeline. Right, there is a difference between how long the simple decoder takes and how long the complex decoder takes. Or, my operations can be served through this micro-op sequencer, or microcode sequencer, which takes even longer. And there's a very interesting paper in this space that explores how you can do Spectre-style attacks using this covert channel. So see, this is an optimization that was created so that, okay, if I'm using the same micro-ops again and again, I can just use it from the cache. But then people figure out this is how you can leak information. Then you can leak information through your branch prediction units. So for example, I can have a particular branch predicting as not taken all the time, and then sometime later it'll predict taken, it needs to predict taken, but it actually predicts not taken. So when there's a misprediction, there's a squash in the pipeline. What that is basically you empty up the entire pipeline and start the execution again. So when you do these squashes, your operations take a lot longer, right? So that's how you can leak through your branch predictors. There are other attacks through the return stack buffer, through the branch target buffer. Basically any optimization you add, you can leak information. Now there are side-channel attacks with the execution units. So as I mentioned before, there are only a few number of execution ports that are available. So there can be contention on the ports if multiple applications want to use port 0, one application will be slowed down versus other will proceed quickly because one will get access to it and the other won't. So that way you can know, okay, my application is trying to use port 0, and that can be a source of leakage. There's the attack using the floating point units, where basically if the floating point unit is powered down, it'll take a long time to power up and the operations will be longer, or if it's powered up, then the operations won't take so much longer. There are attacks through the load buffer, store buffer, where data that is in the load store buffer that will be forwarded quickly, and you can leak information versus data that is not in the buffers. We saw some attacks on caches. Basically, every single unit that you see there, every single block is vulnerable. You can leak information through all of them. There are different cache attacks that you can use. Then you can do attacks on the LLC. You can do attacks on the interconnect. You can do attacks on the DRAM. What this doesn't show is there are replacement logic, which we saw a paper for that you can attack. There's the coherence logic. You can attack cache directories because, again, those are optimizations. There is prefetching, where basically you add prefetchers and they can fetch data that you need, but you can use prefetchers to read random data. Again, that's an optimization that can be, exploited. So even though we just talked about caches, there are leakage opportunities all over this. So yeah, any questions here? Cool. Okay, let's move on to transient execution attacks, right? So modern CPUs are good at optimizing stuff. So they're also good at making mistakes, and they're great at hiding them from programmers. So if you make a lot of mistakes in your microarchitecture, which your chip does all the time, you just don't see it because they're really good at handling it. Mistakes are rare, right? Or I should say relatively rare, because that's how you're able to optimize for the common case. For example, if you're executing a loop 1,000,000 times, then if 1,000,000 times you predict correctly, you'll get a lot of performance benefits. And maybe 10, 15, 20 times at the end of the loop, if you mispredict, where you execute the loop again, but you were actually not supposed to execute it, that's just a little bit of a performance hit. Those are relatively rare. So you can just account for them, make sure that they work correctly. And these mistakes need to be hidden from the program. What that means is these misspeculations that happen, they should not leak into the architectural state, right? They should not leak into your architectural registers. And traditionally, we haven't cared about program invisible structures like the caches, like the branch predictors. We don't care about what happens because we know that eventually we'll get the correct result anyway. And what I mean by mistakes here is basically you can mispredict a branch, right? You can mistranslate an address. You can cache memory, which is not going to be cached, right? And so these are the kinds of mistakes that happen in modern CPUs. And it's interesting, when the Spectre paper came out, if you see the talk in IEEE SNP, the person from Google who was sort of one of the primary people who discovered it, he said that he spent a lot of his time trying to figure out how to make processes glitch, how to make them fault. And then he learned about all this speculative execution, and he's like, the processes are doing it themselves. I don't have to make a lot of effort. I just have to figure out how to exploit them. That's a very interesting talk. Yeah, it's available on YouTube. You should see that. So this is an example of what it looks like. So if you are thinking about this in the Spectre context for a couple of minutes, just forget that. Basically, what can happen here is that if this array one size is say 1 million, then 1 million times I will execute this instruction. Maybe 10, 15 times I will mispredict and execute this instruction, but these things will never reach into the architectural state. They might impact the microarchitecture, but they'll never reach the architectural state, right? And these changes to the microarchitecture are never corrected. So an example of this is that your branch predictors in current Intel processors, they are not trained at retirement. So what that means is that if a branch instruction executes, doesn't matter if it's a correct execution or if it's an incorrect execution. If it executes, it's going to train the branch predictor. Same for your caches. The data is written into the caches, whether it's needed or not needed. right? Because we have created these very nice layers of abstraction between, the hardware and the software, and we give people the ISA to communicate through. So all we care about is making sure that the data that is communicated through that abstraction is good. Whatever happens under that, we don't care. But now, as we've been seeing with microarchitectural side channels and all of these transient execution attacks, we actually care a lot because all of these changes we can observe with very fine granularity. Yes?
Yeah. The way I like to think of it is like whatever's in the microarchitecture is non-binding. If stuff is in the cache or not in the cache, it doesn't affect the correctness of your program. It just affects the runtime. And so people don't recover that information, right? It's just you naturally as an architect think, oh, that doesn't make any difference to the correctness of the program. And so you know, it's just naturally you don't concern yourself with that. Enter Spectre Meltdown.
Right.
It's a new game now.
There's this transient execution attack fallout, which we don't really have time to talk about today. But if you read the paper, they talk about how they read Intel patents, and within the patent, Intel stated that oftentimes they just forward the wrong data, even if they know that it's the wrong data. Why? Because they want to keep the pipeline running. You have very deep, very wide pipelines, and your pipeline sitting idle is just wasted resource. So it's easy to just do, wrong operations, and a lot of the times they just forward wrong data. So yeah.
Who took 470? Remember the load store queue?
Yeah.
When you have an unknown store address, load store speculation is you assume it doesn't match your address, and you grab whatever matches or take it from the cache. That is exactly what Taru just explained. That is a technique that everybody does if they're worried about performance. Because why would you let an unknown store address stop you when, 9 times out of 10, it's never gonna match you.
Yeah. And it's mind blowing. The patent actually says we've just forward data whether it's correct or not.
Yeah.
So in the paper, they called it the right transient forwarding optimization, or the WTF optimization. So I think they were trying to play at like what's going on. Yeah, the Fallout paper is it's a very fun read. So yeah, they call it the WTF optimization or right transient forwarding. They're like, the processor can forward wrong data and you can execute on top of that, and then you can exploit that for fun and profit. So, okay, so transient execution attacks, they trick the processor into executing transient instructions. So what are transient instructions? These are instructions that will definitely squash. They differ from speculative instructions because speculative instructions may or may not squash. So transient instructions is just a subset of speculative. So this is like, if you read more papers in this space, now you know the terminology. So they trick the processor into executing transient instructions, which leave microarchitectural traces. That's the core idea behind transient execution attacks. There are several examples: Spectre, Meltdown, Foreshadow, Riddle, Fallout, LVI. And this is what the landscape looks like. We won't spend too much time into it, but basically you have the branch prediction side channel on the top left, where basically you can train the branch predictor to do something, and in the case where it's not doing something that you need, the operation is slower, you can leak some information at a very high level. And then you can use these branch prediction side channels for Spectre, where Spectre is basically a confused deputy attack. What that means is you trick your program into running some code which it wasn't supposed to run. And the example of that is within that branch code sequence that you saw earlier, and we'll see again. You can execute the line within that if statement transiently, right? And it'll leave data in the cache. Then there are meltdown style attacks, where what happens is you have the faults or the exceptions which the processor raised, right? If you access something illegal or if you forward the wrong data. These just are, the exceptions are delayed, basically, right? And that's because these exceptions are raised when the offending instruction retires. And it retires much later. Like you cause the speculation, you run the instruction which causes the faults, but it's raised much later. So the instructions following the fault are still executed. As programmers, we wouldn't care because we will never see the wrong results, right? And at retirement, we'll know something went wrong. But as attackers, we'll figure out that some changes happened to the microarchitecture, and now we can leak it. There are several attacks in this space. There's Meltdown, there's Foreshadow, there is MDS attacks, which is they are looking at random buffers in the microarchitecture and trying to leak data. There is Zombie Load. We don't have time to go into all of them, but we'll talk about Spectre and Meltdown. And the last class of attacks, which is relatively recent, is called LVI, where they basically execute Spectre-style code gadgets, but they combine it with the Meltdown-style leakage, where I know it's like super abstract, but if we have time, we'll talk about it. But yeah, but I think you'll know enough by the end of this talk that once you look at the LVI paper, you should be able to understand it easily. Okay, so transient execution attacks need 4 components. This is terminology, like in the dark blue, this is terminology which Microsoft Security Response Center proposed, and it seems to be very popular in the community, and that's what we'll go by. Okay, so I'll talk about these things that you need in the context of this Spectre V1 code. So in Spectre V1, basically what you'll do is you'll train the branch predictor to predict this instruction such that this line executed. How do you do that? You execute this branch several times with x smaller than array1 size. Sometime later, you'll give it a very big x, which points somewhere way out of memory towards secret data that you're interested in leaking. And your processor will predict this branch such that line 2 needs to execute. It will predict it. It'll be a wrong prediction. It'll predict it. You'll execute this instruction, and you'll leak some data. Okay, so first thing what you need to do a transient execution attack is a speculation primitive. What this means is you need something which will take the processor down a speculative path, which will cause a speculation. So a very good example is just conditional branch prediction, right? The processor will say, okay, I predict this such that this line 2 will be executed. I predict it as taken or whatever. You can also do speculation on indirect branches, right? Where basically you're trying to compute the target, but the branch target buffer will just give you a random target or a trained target which you can use. So that is another way to cause some speculation. There can be memory disambiguation. As Todd mentioned, there are stores and loads. So what you can do is you can predict that, okay, this store is going to forward this data to the load. So now I'm in the speculative path. And then there is delayed exception delivery. Basically, you execute an instruction which causes an exception, but you raise the exception much later. So during that time, you're in the speculation. So the first thing you need is speculation primitive. So in our case, if x is less than array1 size, this line 1 is the speculation primitive. Then you need a windowing gadget. What the windowing gadget is it's something which provides enough time for this line to execute, right? So an example of a windowing gadget would be if this array1 size, if this is not cached, right? If this is not cached, then my processor can't immediately execute this. And in that case, I'll basically have a very long speculation. Another option is I can create a very long chain of dependent arithmetic operations. So for example, if this x was a result of several floating point division operations, right, which take a lot of time, in that case, it doesn't matter whether array1 size is in the cache or not. What will happen is that x will take a long time to compute, and the processor will say that, okay, the last, say, 500 times, I predicted this as correctly as, this thing was, this branch was taken. So this time also I'm going to predict it as taken, even though x hasn't been resolved. So you need a windowing gadget which can make sure that this thing takes time to resolve. Okay, and then you need a disclosure gadget. What a disclosure gadget is basically it accesses the secret, right, which this thing is doing, just array1 of x. That's it. It accesses the secret, and it prepares it and loads it into the side channel. So this array2 is the actual side channel here. What's going on is, I don't know what this array1x bit is, right? It's just, this byte is. But what I'm going to do is I'm going to make a dependent operation on array2. And then I can figure out which elements of array2 are loaded quickly versus which elements are loaded slowly. And we'll see an example of this a little later as well. So this is the disclosure gadget, array1 of x and its multiplication with offset. And then finally, you need a disclosure primitive. Now that your transient execution attack has leaked data into the microarchitecture, now you need to retrieve it somehow. And you retrieve it how? Using your using the microarchitectural side channels, which we saw earlier, prime and probe and flush and reload. And this was, I think, also a question on the exam that, like, how do these side channel attacks, facilitate transient execution attacks? That because That's because you need these side channels to actually leak the data which was stolen by the transient execution attacks. Any questions on this, on the terminology? Yeah.
So for the speculation primitive,
Yes.
does it change in any way if like, let's say here the if statement is like nested, there's multiple conditions, so is the execution any different, or does it try to just meet those conditions?
In that case, yeah, that's a good question. In that case, it will try to meet those conditions, but then you will have to make sure that if you want to reach a certain instruction in the nested ifs, you want to make sure that all of your branches predict correctly. Right, so in that case, your speculation primitive will be like, you want to make sure all of those are predicted in certain way that you end up at the instruction you want to execute. And your windowing gadget can be basically all the operands for that branch. For example, if, for example, array1 size in this case, you just kick all of that out of the cache and you figure out, okay, what's going on. It'll take a long time to resolve. Does that answer your question? Okay, great. So yeah. So this is the Specter attack, where basically you trick the processor into executing wrong path instructions, and you leak the data from within the same address space. So note that no matter how large my X is, it's still going to leak data which is in my address space. So that's, that's the key idea behind the Spectre attack. You're leaking data from within the same address space. So there are several variants of this. Variant 1 is the bounce check bypass, the example of which you see up there, where basically you have a bounce check and you bypass that, you access memory beyond the limit which you're supposed to, and you can leak it in the channel. There's another variant, which is the BTB poisoning. So here the issue is that your branch predictor, you don't access it using the full 64-bit address. You access it using a part of the address. And why do you do that? That's because you need the indexing logic to be small. Each bit you add, right, is going to increase the size of the branch target buffer. So what you do is you index into the branch target buffer using only a subset of these addresses, say in the lower bits. Now what can happen is these lower bits can be same for two different branches, but they're actually different branches. So in that case, you'll have contention in the branch target buffer, and you can cause your program to execute the wrong sequences. So I don't know if that's super clear. Let me actually draw this as well. So yeah. So if I have some address where the upper bits I don't care, and the lower bits are like let's say A, B, C, D, and then I have another I have another branch whose address, the upper bits are different, but the lower bits are A, B, C, D. What I can do is I can train the branch target buffer such that I can make A, B, C, D always predict to say address P. And then what will happen is when this different address comes into the branch target buffer, it's only going to use these lower order bits, and it'll look at the entry which was not trained correctly. Again, this is a prediction. This is not going to be seen by the program. All the program may see is like a faster execution or a slower execution. So it'll take the same target P where it was supposed to go to Q, and during that small window, it'll start executing code from location P instead of location Q. So it takes it into a speculation primitive. So that's basically what the variant 2 of Spectre is. There's another variant called variant 4, which is store to load forwarding. That is basically you have some prediction going on in the memory disambiguation unit. And then there is read to spec, which is basically you're in that case, your speculation primitive is the return stack buffer. Basically, that is again a buffer which is invisible to the programmer, right? You just you can write some addresses which will be used as predictions for returns, for function returns, and I can overwrite it to make it jump to whatever location I want, and I can make it execute from there. And how can I increase this by kicking? How can I increase the duration by kicking the operands of a particular instruction out of the cache? So the speculation will take much longer to resolve. There is no variant 3 because variant 3 is technically Meltdown. So, that is just something to know. So let's look at a code example. Let's see what it looks like. Let me see if I can. So this is an implementation, there are several implementations which are available. This is, I think, adapted from the original implementations which the Spectre authors proposed. So an important thing so the key thing to see here is, this is my victim function. This is the gadget which I'm trying to execute, which I'm trying to leak, right? So that's it. So and this is trying to leak from the same address space. This is a very simplified example, but okay, I have this array 1, which is, which has this, it has some size, and I have the array 2. It has 256 elements, times 512. So this 256 basically denotes the 256 possible bytes from 00 through FF, because we don't know what the secret byte is, right? So that's what, that is the unused stuff that is just used for padding to make the attack easier. This 512 is basically some cache padding so that you can fit your data neatly into the cache. That's not super relevant. And this is the secret that we want to leak, right? They just call it the magic words are squeamish or afraid, right? And this is the data that we want to leak. So what we will do is basically, we will execute this line of code. A lot of the times we'll have a small x, like x which is smaller than array 1 size, and then sometime later we will have x which is much bigger, and it points to this location. It'll first point to T, then H, then E, and so on. And then at that time, we won't know what the exact secret bytes are, right? Because that's what we're trying to steal. So basically, we'll take the secret byte, T, whatever it is in hex, and make a dependent access based on that. So that cache line corresponding to, whatever T is in hex, let's say if it's AB or whatever. So array 2 of AB, like out of 255, that particular line will be in the cache. So that will be accessed quickly. And we can see the driver code at the bottom where basically what this program does. And this is sort of the standard implementation across several, several different people have implemented in the same way, because people have figured out this is the optimum way to do it. Okay, so what are you doing here? First, you run it for 1,000 times. I want to run it for a long time so that I can leak information. Then here, I'm flushing my array 2 out of the cache. All the possible 256 secret bytes, 00 through FF, I'm kicking it out of the cache, right? So if it's out of the cache, then the next time I access it, it'll be accessed slowly because it needs to be brought into the cache. But my victim function would have executed before. One of the secret bytes, say corresponding to T, when we are trying to leak T or then H or then E, that will be loaded into the cache in advance. So whenever I time it, right, that thing will be present in the cache and I will be able to access it quickly. Does this make sense so far? This is your, the flush reload type attack. So I'm just flushing data out of the cache, and then I will just check at a later point which data was loaded. Okay, so then what I do is I flush array 1 size out of the cache. Why? Because we want to create our windowing gadget, as we discussed. We will cause a delay. Why? Because we want this CL flush instruction to complete. You can run this code on your machines and it will leak the data. And if you comment this, sometimes it won't leak the data. Why? Because the CL flush instruction, there is no strong ordering, right? It will realize that, okay, I am using my array 1 size again, so let me use the array 1 size and then flush it. That's not what we need. We need to flush it in advance so that we are able to create a long speculation. Does that make sense? Okay, good. So, you do this delay, which is an empty loop. You can also write mfence, whatever that works. Now this bit of code. So what you can do is when you run it yourself, you can just print it and figure out what it's doing. But basically the idea is that for 5 times, it'll set this X to less than array 1 size. And on the 6th time, it'll set it to some malicious X. That's all it's doing. So it's doing this complicated stuff because you don't want to tip off the branch predictor. You don't want to start the prefetcher from running. You want to make sure that your accesses are truly random. Okay, so that's the idea behind this part of code. If you, before this victim function call, if you just see out your X, you'll see exactly how it's doing that. It's very simple once you print the code. And then basically this is just my flush reload covert channel where basically I'll say that, okay, so they call it a mix-I, where basically you mix up the order to prevent any prediction. Because if you add some prediction, then some data will be brought into the cache, and you will access that quickly in addition to the data that you leaked. So you don't know which data you eventually ended up leaking. Does that make sense? The only thing you want in the cache is the data you actually leak. So you just do it in some random order. Then you figure out that, okay, this particular address, I will time how long it takes to read. So here I'm just calculating the address. I will say, okay, so RDTSCP is just an instruction in x86 which gives you the cycle number at that time. That's it. Then you dereference that particular address to load that memory. This is memory access to time. And then you do that timestamp counter access again and subtract it for time 1. So what this will give you is how long it took to read that particular cache line. Read that particular line. So if it's already in the cache, it'll be accessed quickly. Why is it in the cache? Because my Spectre V1 gadget brought it into the cache. If it's not in the cache, this is going to take some time. And you can play around with cache hit threshold values, and basically it's doing some more fancy stuff, which you can spend some time reading to basically tell you what's the bit that is going to be leaked. And that's it. That's the simple idea behind a Spectre V1 attack. So this is a simple implementation. So now if you see code like this, you will know exactly what's going on. Any questions on this? All right. Let's go back to our... Okay, then we have the meltdown type attacks where Intel made, and I use this in quotes, a design decision that, okay, we'll raise the exceptions much later than they're actually happening. We'll raise the exception once the instruction retires, and we let the subsequent instructions execute, because if we predict correctly, then yeah, we'll get a performance benefit. If we do not predict correctly, there will be a small performance hit, but A, that'll be rare, and B, that'll be never seen by programmers. So let's do that. AMD did not make this design decision. So that's the main reason why Intel is affected by Meltdown and AMD is not. There are other variants of Meltdown where, various processors are impacted by varying frequency so that you can, look at the particular papers and figure out what's going on. So here basically, so because your exceptions are raised only when the faulty instruction retires, your subsequent instructions are executed in a transient manner and they leave information in the microarchitecture. So this is an example of the meltdown attack where basically you access the kernel memory with this kernel address. I am not supposed to be able to access this address because it's mapped by the kernel. As a user space program, I can't access this. It should give me a fault or an exception, which it does. But I will predict, but I will raise this fault much later, right? When this instruction actually retires. So during that time, will I let my processor sit idle? Nope, I will execute the next instructions. I will take this kernel memory, multiply it by some random offset. In the Spectre example we saw, that was 512, here it's 4096. And basically, you make a dependent memory access in a probe array. And what it will do is it will leak kernel memory. It is really that simple. You're just writing code, which programmatically you will never see the results of. But because of how microarchitectures are designed, it will leak this data into the cache, and you can do your standard flush reload attack or whatever we saw in the Spectre V1 example before. You can do that to exactly read kernel memory. This is insane how simple it was once it was discovered. Meltdown has been fixed now, but the core idea behind that remains valid. So yeah, so that's how Meltdown works. And let's move on. Okay, so there are several other papers. These are some high-level defense strategies that are used. So before that, let me just clarify some terminology. So the paper I pulled the defense strategy from, that has this access, use, send process where basically I'm accessing kernel memory. I'm using it, I'm making this multiplication to put it in the covert channel, and I'm sending it by putting it in the cache. That's just the basic idea. So there are several defense strategies. One is you add some isolation. So what that means is that programs across different domains are isolated. So even if you're leaking data into the cache, There is no contention in the cache where data has been loaded and you can time that, okay, it's accessed out of the cache, it's accessed quickly. If it's not accessed out of the cache, it's accessed slowly. So you just isolate either parts of the program, isolate the cache, isolate the branch predictor. There are several places you can add isolation. So that's a defense strategy. Right? And this is an SOK paper. If you don't know SOK paper, it's like systematization of knowledge, where they basically take a look at a bunch of papers, find out the common themes, and arrange the information in such a way that instead of having to read those 50 papers, you can just read the SOK paper to understand what's going on. Okay, so there is no set. You can add isolation. You can do this thing where you can't access the information that you need. So, for example, that memory access that you make on the secret value or on the kernel memory, this particular work prevents that. Then this says that, okay, if I'm loading data speculatively, I'll make sure that I don't use it, like I don't multiply it by an offset, or I don't put it in a particular covert channel. There are several ways to do that. And then this no send is basically saying that, okay, I can, again, either isolate my structure so that I don't leak data into a shared structure, or I can say that, okay, if I'm within speculation, I will leak data to a shadow structure. What that means is there's an additional structure, right? And I will make my temporary updates into that structure. And once the speculation resolved, I can move it to the main microarchitecture structure, like the cache or the branch predictor or whatever. So that's a way to stop it. You can delay, basically, you're saying that, okay, we'll delay dependent operations until the speculation is resolved. There are like several defense strategies, and I think now you're well equipped to just read the paper and understand at a high level what they're doing. So yeah, and basically what you want to do is, of those 4 things that we discussed, speculation primitive, windowing gadget, disclosure primitive, you need to block at least one of them. And if you do that, you are protected against these attacks. Okay, so we are nearing the end here. So if you want to look into this area further, this SOK paper where I pulled the figure from, it's a very interesting read, right? That'll be a good thing to check out. There's this website called transient.fail, which basically, I can actually show you, it'll take a second, but it's a very nice organization of different like Spectre and Meltdown style attacks. Let me turn this off. Okay. So if you go to this website, it'll show you, okay, that what's my transient cause? Is it Spectre type? Is it Meltdown type? And then there are different what's going on? Yeah, there are different microarchitectural structures you can leak data from. Pattern history table, which we saw the conditional branch prediction, the BTB, which is the branch target buffer, return stack buffer, store to load forwarding. Then there are several places you can do meltdown style attacks from, and they can be in the cross address space, same address space. And if you click on these, it'll show you the description and a particular paper which exploits that. It explains why certain attacks happen. This is a very good site to sort of get a high level idea of these attacks. So transient.fail, that is something you can check out. Moving back, there is this repo, it's called Mastic, which is basically a microarchitectural SideChannel toolkit implementation. That is something, I don't know the exact full form, but this was created by people who work in the space, and you can find some good implementations of prime and probe, flushed reload attacks there. This other this other GitHub repo that exists, this provide proof of concepts implementations of various transient execution attacks beyond just Spectre V1 or V2 that we discovered. It has a lot of options, and you can check out their repo for other papers that they have mentioned. So a lot of those papers have proof of concepts, and they are available publicly. Okay, so conclusion. Microarchitectural side channels, they require data-dependent utilization of shared hardware resources. If you have just one of those, you can't leak data. You need to have both of them. And these microarchitectural side channels are abundant. Any new optimization that you put in your microarchitecture is a potential leakage source if it's doing data-dependent utilization of shared hardware resources. So these are abundant. We just looked at caches, but in that giant figure that we saw, there are several other places to leak from, whether it's your front end, whether it's your back end, whether it's uncore, that is stuff which is outside the main core. Now, and then transient execution attacks, what they do is they trick the processor into executing either unauthorized instructions or illegal instructions or related memory accesses. And these things leave microarchitectural traces, right, which are not cleaned up because they're very expensive to do. In that SOK paper, there's a paper that they cite, it's called, I think, Cleanup Spec, where basically what they do is after the speculation is complete, they figure out it was a misprediction. They're like, okay, we're gonna go into the cache and clean up whatever data was put into the cache. So that's, another way to defend against these kinds of attacks. So yeah, transient execution attacks, like, they leave microarchitectural traces. And another important thing, your microarchitectural structures, like your return stack buffer, your branch target buffer, pattern history table, your caches, your prefetchers, everything, or most of the things right now, they're trained at execution. They're not trained at retirement, right? They're trained at execution. Why? Because a lot of the times my execution is correct. So I want to get all of those performance benefits. Training at retire would definitely have a performance hit. Like that is also something I was exploring at my internship. So yeah, training at retire is expensive, but I don't know, maybe in the future they'll figure out that, okay, we actually need to do that so that we don't leak data. And then finally, partitioning, isolation, encryptions, these are all durable defenses, but they are very expensive for now, because we haven't designed our processes according to isolation or encryption. So I believe that this is like good motivation to design stuff so that we can isolate stuff, we can encrypt stuff, we can partition it. And that's all I had. Any questions? Right.
Within 10 years, when will we stop these attacks?
We won't. I think the idea is that the stuff that you really, really care about, you'll execute it in a data oblivious manner so that you don't have data dependent behavior, or you will encrypt it so that you're not, so that even if I am able to steal some information, it is just garbage to me, right? If it's encrypted, it doesn't matter what it is. I need the key to decrypt it. Or people will figure out that, okay, these are not that big of a deal, and we'll be like, okay, we'll worry about other attacks which are a lot more important. So these seem to be really hard to stop unless you're willing to pay the performance penalty.
So you're saying the way to win the game is to not play it up.
That's a great way to put it, yeah. Like, yeah, I can change my threat model, I can change the game. I'm like, yeah, it's an attack, but I don't care about the attack, so doesn't matter. Yeah.